compute will be abundant in the world because we have machines and we have humans, and humans can make machines and we can create data centers. So maybe we should not solve for context, we should solve for how to provide our own context. So the question, or the best thing these transformer does, is they helps you solve one problem, which is how to find what is the next thing in a sequence. This is how machines understand language. They create embeddings, and once the embeddings are created, they could figure out which word is closer to what word. Now you know a little bit about transformers. Transformers allows you to do scaling of self-attention. They have this idea of attention, which allows you to figure out, given a set of words, which word are important and which words are not important. So that scaling law says that the larger or the more attention layer, the larger the neural network you put, the more things you can learn. That means we have a small feeling of AGI in our hands. Then we will be able to elevate humanity to one step forward or push them to think even harder because we are coming and thinking like them. That means maybe it's not an hype and maybe I should stay happy. And now you can make your choices for products too, based on the information we have. Good morning. Today's session is about transformers. My name is Mahesh. I will be taking you through transformers. But before I go to transformers, I want to tell you why even transformers are important for all of us. Why should you care about transformers? What is the answer? It remains that central topic, to be honest. Like when I look at it, everything, if I need to explain any technical idea or anything like even planning idea, for an example, when we started, one of my uh, close friend brought me this idea that, hey, we should solve for context. The world has a context problem because when 2023 GPT 3.5 came out, the context window was 16K or 8K, right? Because that was GPT 3.5, the context window. How many words can you send is 3.5K. That means you can send 3,000, sorry, 16K. That means you can send 16,000 words. Words even are broken down into something called tokens, which we will talk about today. But the idea was that, hey, how can we do this? And I looked at it and I said, you know what? That's a compute problem. And compute will be abundant in the world because we have machines and we have humans, and humans can make machines and we can create data centers. So maybe we should not solve for context. We should solve for how to provide our own context. So he didn't listen to me. In this case, it turned out that every 3 months, we have increased the context size from 16K to 64K to 100K. And that was, if you remember, when Claude came out. Remember Claude? Anybody knows what Claude is? Claude is Anthropic's largest, biggest model, which they also offer to compete with ChatGPT. And their wedge was that, hey, how can we go and say we are better than ChatGPT? They said we will spend more money and we will give you a context of 100K, which was unheard of. Like 16K was so like big. But do you know like why increasing the context size is so hard? Why should we worry about it? Why Chat GPT Maker? By the way, Llama when came out, Llama, remember the disaster that gone through for Facebook? Remember Llama? Llama's first model 1.0 had 4K context only. 4K means 4,000 words. That could be if you have like that's 2 to 3 pages. That's it. GPT 3.5 was 3.5K. This is GPT 3.5. And suddenly, Claude came up with 100K. And then Gemini, and this is just timeline wise different, right? So this is, let's say, 2022. This is 2023. I think this is late 2023 or 2024. And they said a million context. So now we are increasing the size, as I said. And if anybody said that I can build a model with a larger context, they will be out of business. Why would they be out of business? Why is so hard to increase this context? Anybody? Because we say we need not to run technical stuff. By the way, disclaimer. Today is a lot of things I'm going to discuss today may not be needed for your day-to-day job, but these are awesome things for your lunch meetings, for your hiring managers, offline discussions, or to build a lot of trust in your engineering teams. So if sometimes you feel like it's going too far away or it's something you need not to know, most probably you are right. But most of the decision, these are the first principle thinking. If you want to have a first principle thinking in AI, the learning that you will take from today's session will be very important, and it will have you decide whether you should, where should you play, what are the limitations of the current state of art architecture, which is transformer, and it will help you answer the basic questions like, hey, is hallucination a feature or a bug? Why can't model reason? Why can't we have infinite context? All these are good questions, right? And today's session hopefully will address those, but none of them is directly proportional to what you need to do to your day-to-day product development, evaluations, finding the right opportunities for AI, finding risk in AI can be done without answering these questions as well. Good. So just know that if you miss me sometimes or if you not follow along, I will try to today. I have dumb it down. Hopefully that helps. So let's see how this one lands. But the idea is, first question we are trying to answer to us is, why is it taking? Why can't we just say infinite? So let's say we want to solve. That's an unsolved problem. That the larger the context, we have this hay in the needle stick, finding needle in the haystack, right? That the more the context, the harder it is. But let's say they are solving it somehow, and if they don't solve it, yes, we have a problem. Ricardo, then we will move on. I just wanted to plant a question in your head, and hopefully in this session we will be able to answer it.
Yep. Mainly is the attention block, because it's a quadratic scaling, and every parameters that we add, it's quadratic, and that's the most important part of the transformer that is consuming more resources. So if we are able to have a much more performing attention block, we can actually have a better transformer with less cost.
I think Ricardo has the most engineering explanation and the most correct one. But let's see. Hopefully, we can get to some dumbed down version of it. But correct. The idea is that what he used is the word attention. He used the word quadratic scaling. That means that every time you add a word, you have to take it to the power of 4 compute, because you are calculating every time you add a new word to the context. I have to start training 4 times more. I have to spend 4 times more. And you keep multiplying that every time. The larger the context, the larger the cost grows 4 times. If you do other training, which is let's say you are saying I'm going to increase the size of model, then the cost is increasing linearly. The larger the model size, the more the cost. So if I go 10x larger the size, the 10x is my cost. But if I go in the context window, then my 40x is my, if I go 1 to 10x, then I have to take a multiplier of 4 on top of it, right? So that's why this cost, people are saying, hey, customers are not complaining about a lot of context. This is big enough context. So why spend 4x more or have a quadratic scaling? If I want to increase the context size, I will just spending here, because at least here linear scaling. Good. And that's why we have seen that the context has not grown as much as the sizes has grown, because of this linear versus quadratic scaling. The more context you add, the more compute, proportionately 4 times more compute you need to add. And that's somewhere hidden in how attention is coded or how attention works. And that is the question I will leave up to you. I won't be able to answer it today, but I will leave you to this question in or curiosity in your head, that why it scale quadratically in context. So I leave you with that. Okay. Second question, which is also, so context window, one open question, why it scales 4x. At least we know the answer, which is like, at least it's quadratic. So it's 2 to the power 4. If you increase the context size, that's why increasing the context size is a little harder or more expensive than increasing the size of the model. And that's why we are saying that we will increase the size of the model first and then increase this. So at least we got one answer. We are very smart in that chit chat with some engineering or some smart people who know transformers a little bit. By the way, already you're very good. So hopefully by end of this session, we'll be more good. Another thing that is open question I want to leave it is like, one question more I want to discuss, which comes up a lot, is can these models think? Are they thinking models? Can these models think? This is a debate always, right, on internet. Hey, we don't have reasoning, we don't have thinking power, transformer have their limitations. This is not what it is. This is a hype. Because this question leads to, can model think or reason? Because this question connects you to this question of hype, which connects you to this model of AI as a next.com, which connects you to your worries in life. This is me. So this is another open question, which hopefully this transformer, understanding transformers, can answer that for you. Next question is this idea that why now, which you get in a lot of parties, or if you go to birthday parties and if you claim that I am the AI instructor, I teach a course, then people will come to you and ask this question like, hey, what changed? Why now? What is like so different in the world that people are getting crazy with AI? AI is there for 100 years. What has changed for AI? So why now? And what has changed in AI? What has changed in predicting, or AI or machine learning is predictions? How we changed? What changed or how changed? What changes made it possible? Can you answer that succinctly? So today is very engineering focused session. And the goal of today's session is that we can all come to some kind of fundamentals, and we can learn these fundamentals so that we can answer these more long-term questions or some short-term worries that we have. Good? If that's clear, I will be using a lot of visualization. I found this yesterday. I watched a whole of Blue Brown videos. I read the paper again, and then I was trying to use my analogy, which I used last time, on How I Met Your Mother. But then I said, no, we're not going to do that. So I left that, and I found this. So we'll do like first the 101 version, and then hopefully I can get to 201. But let's see if we can make how we do on the 101. And hopefully this 101 gives us 90% of what transformers are, why they are successful, how they work, and all that. To get to transformers, can I get to tokens first? So can we all understand one more thing, which is tokens? We know words, we know characters, we know words, we know sentences, we know paragraphs. Then what the hell is this token thing? So tokens is a way to represent a unit that is consistent for model training. Let's say we say this way, right? So this is the word, my name is Mahesh. It has some columns, some paragraphs, some question marks. And if you can run it, there are online versions that you can run it, and they will give you the tokens in it, which will generally uses 2 or 3 principles, which is 4 characters are generally 1 token. So if I have my with a space, then you will get 1 token right here, then this token. And if you have some dot, then it will be considered as 1, then this one, then this one, and then hopefully this one. It's a uniform way. It's provided a uniform way. It is always like kind of similar size, or kind of some, if I break them down, these tokens are mostly same wherever my and space will be. And then we can learn how these go together. The question is, why tokens? Why do tokens, and why do tokens at such a small scale, not like sentence level? So let's park it, and hopefully after the session we will know. So today, for the first 101 on this, I will be using these visuals that FT put up, Financial Times. This is the one thing that I found the best way to explain transformers to 101 session. Then we can go to 201, because this will leave some questions unanswered. But I think if you understood this much, you have everything that you need to learn as product managers about transformers. So let's go in this, and then we will go. Transformers are amazing. That's all that article said before that, so don't worry about it. So the question, or the best thing these transformer does, is they helps you solve one problem, which is how to find what is the next thing in a sequence, whether that is a sequence of an audio, sequence of a picture, sequence of a word, sentence. Good. That's the problem they are trying to solve, which is what is the next thing in a sequence, which can be sequence of sentences, sequence of audio files, sequence of pictures, so that we can have videos like Sora 2, VO, and all those models. Good. To write, LLM must translate word into a language they understand. So the first step to predict the next word in a sentence, you need to put things in a machine format. And first step of that is you put them into tokens. So I take whatever I got and I create these tokens. So now I have 6 tokens out of this sentence. Everybody same page? We take words, we convert them into tokens. But as somebody rightly said when I was talking to you, we don't understand words. We understand words, but machine don't understand words. We need a language in which machines can understand, and machine can understand only one language, which is 0 and 1s. Correct? So how can we convert this word work into some kind of 0 and 1s which have the context of this word? That's where embeddings comes in. So what is happening here is we are training that how this work comes across in different words and what is the kind of relevance this has to other words when we use the word work. You can see it in these sentences. We can delegate work. Work is so hard. Work, his dedication to work has impressed everybody. All those things. We are looking at work and we are saying what can go closer to it. How the work is related to the other words in English dictionary. And this data we already have. So we can train this on nearby words. If we can train this, then we can find work relates to office, work relates to at, work can be downtown, work can be project, but work and atmosphere, work and zebra, work and dove, and work and polka have no significance together. So we can find work and what work relates to and what work doesn't relate to by just going through a lot of text on internet. Can we all do that? If we can all do that, then we can put all this information as zeros and ones and encode that in a 2000 column matrix or this vector. And this vector can ultimately result what work would be. And we call this work or this vector as embedding of the world. So that's the first step. In any AI, you need to convert this words into something that machine can understand, which is numbers. But these numbers are trained based on how the work relates to other numbers or other words in English dictionary. So far, so good. You got 20% if you got embeddings. Everybody got embeddings? If you didn't got, just put some questions on chat or in your notebook. We will talk. We can come back to it. So now I have done the first step, which is I took the sentence, I converted it into tokens. For each token, I have created an embedding, which is this value. Then I have work and I can find embeddings or the value of work. But then if I can do that, I can find the values of other words too. Sea, ocean, football, soccer. And you see one pattern here that the things which are common, which have a lot of things common, their embeddings, if you color code them, would look very close. Like sea and ocean look close, but sea and football doesn't look close. Because these numbers on each column, if I color code them from this pattern, then they are related because they show up together combined to other words. Good. So if I am training how sea and ocean show, they are showing closer by, and that's how I calculated these numbers in these columns. So these numbers embeddings look similar to the numbers that, or to the words that it came across or we have used before. Good so far. We have embeddings. Embeddings allows us to put the context of language in words, but in numbers, in numerical form, the words. And it also gives you this power that now similar words will have similar embeddings. If that's the case, then what you can do is you should be able to go and say, hey, if I put all of this on an XY axis, then I can see that the words that are closer will stay closer. Then I can cluster them also. So all pronouns in this are clustered together. All the motion verbs are here, and then nouns are here. And nouns also, the nouns which represent similar things are here, while the nouns that represent other things are here. So now machines can understand language. This is how machines understand language. They create embeddings, and once the embeddings are created, they could figure out which word is closer to what word. And that has a meanings of noun, also verbs, and also adjectives, but also how these other adjectives that we use, if they explain the same thing again and again, those can be clusters again. This is just two-dimensional. Generally, the embeddings have 2000 dimensions. Umesh is only following me. So I will just keep it following Umesh leads. Anytime he says thumbs up, I will keep moving. Okay. I think all of us are getting that. Embeddings to this kind of representation. Great. If we can do that, maybe that's all we need. But there is a major thing, which is attention. So, okay, now we know the words as embeddings, but we get sentences, right? And if we get sentences, then which sentences in a sequence of which words in a sequence of sentence I should care about, and which one can I ignore, is another thing that I need to learn to predict the next word. Good. Because if I have to predict next word, I can go back to that map that I showed you earlier, but I can't take everything. The context window had 100 million words in it. If it has 100 million words, I can't take all of them. So I have to focus on few words. And how to find which words to attend or focus on is the idea of attention. Okay, so I will figure out which word I should attend out of these 100 million or 4,000 contexts or this in this sentence, and I can ignore which one. The better I can encode that attention, the better my capability to predict the next word. And that's what the second and the most important idea here, which is encoding attention. So the idea here was how to figure out which words should I care about. And this is the way before transformers. This is a recurrent neural network. What they did is every time they calculated the next word, they used the next word to predict the next word. So if I have to predict no, then they took care of interest. Then they took in, they feed it again. But the problem is when you reach to politics, by that time you lost the context of I have. You're seeing that? So I can only keep a limited window. And second problem with this is that it cannot parallelize, because if I have to calculate politics, I have to calculate first in values and then politics. So I have to go serially step by step. So two limitations of this architecture, which is where transformer shined. So transformer said, hey, I can give you something called self-attention. What is self-attention? I can find a value of myself, and that value somehow represent where should I pay attention to and which ones I should not. And I can do that parallelly, which is this idea that a self-attention looks like this. If I say I have no interest in politics, I can just go and talk to every word before everybody forward and figure out, am I related to something or not? And then each word can do that at the same time. So I can go, I have no interest in politics. This is serial. But if I give this word to self-attention or transformers, they will calculate for each word at the same time. This is the breakthrough. The breakthrough is I can calculate how is this word important to other words at the same time while this word is calculating how is this word related to others. So what interest should attend to? Similarly, have is figured out who should I attend to. And at the same time, that is one unblock that attention gave. Good. If you're only taking one thing away, just take this away that I am figuring out which should I attend to. And while each word is figuring that out, it's figuring it out in parallel. Just take this away for the time. Okay. So now I have self-attention. With self-attention, what can I do? In this way, I can say, in this example, I can say the transformer interest is being used as a noun. So that's all it figured out, that I am a noun. Why am I a noun? Because I am paying attention to I, and I'm not paying attention to politics, let's say. So I have no interest in politics. So it said I am going to be more focused on I and politics, and I'm ignoring have and no. That's why I am. But if it says the bank interest rate rises, then it figures out in a financial sense. It's no more used as a noun. It's a financial number or term. Good. How? Because it pays attention to bank, it pays attention to rate, and that's how it's got here. But now if I combine them, then you see the blue dots here represent where it's paying more attention to. So if it finds out that interest has to pay no attention to of than the, about and the, but has to pay attention to no and I and in, then it can say, okay, I'm a noun here. But here, I need to pay attention to bank, which at this point, when this value gets calculated, these ones it's paying most attention to. This no and in, I and rising. That's why it thinks it's a noun. But then if it switches to this interest rate, then the attention goes to rate and bank. And that's why it thinks that, okay, now I'm the bank one. Good. So now what you can do is you can distinguish two things and you can say, hey, when you calculate the next word here, this interest is attending no, so this would be in, but in this case, the next word will be rate because the attention is paid to rising and not to I or no or in, the most is rising. Okay, if we have a way to do that, then when we go and summarize these things, this idea says that when we replace these words, we can find the next common close by words. When you replace this word interest, you find enthusiasm, you find encouragement. While if you have to replace interest, you will replace it with profit or dividends because these are the closest word in the embedding that we learned earlier, right? That two plane thing. So if you can just, when we do summarization, these models do summarization, right? So when they replace these words, they found different kind of words based on their relationships. Then if we can find that, then it doesn't only apply to these single words. You can just say, then you can also find the same thing. Right now, we just saw that how attention help us distinguish interest and detect two different kind of next word based on where they pay attention. Similarly, we can use the same idea to find out what this it refers to. If it refers to chewing the dog, then the word will be different. If it refers to the bone, then the next word will be different. Let's see that. So let's say we say the dog chewed the bone because it was hungry. And if you check the self-attention on this, in this case, the it is paying attention to dog. And that's why the next word hungry, and for get to hungry, it needed was. But if you change the word hungry to delicious, then it is more about bone and not about dog anymore. So now it refers to the bone and not the dog because this word changed. Good. And similarly, if you have to detect the next word, if bone is what I'm paying attention to and I have it here, the most likely next word has to be delicious and not hungry. So you saw how the paying the attention backward or knowing where to pay attention allows us to better find the next words in a sentence. That's pretty much all this self-attention is doing. And it is doing it in parallel so that when bone is, it is calculating its numbers, bone is also calculating where bone need to pay attention to. And based on that, you know, if you are calculating next word by it, then you know where to pay attention to. If we have done that, then if you know how to pay attention and calculate the next word, this is your ChatGPT. You can just continue doing this simulation next. You keep getting the next word and then you keep calculating backward, which word, and that's it. This is how ChatGPT works. This is how GPT model works. It just keep pretending the next word based on the attention that it need to pay, which word it needs to pay attention to in the previous word, and then it finds the next word in the sentence. So if you look at the architecture of transformers, it is the neural network which is depicting what word you should pick in the dictionary, but the attention layer here are figuring out where this word should come from. So it's nothing, this is a very simple architecture. You put your inputs, which is all your sentence or all your context. I go and create an embedding of that. Then I add where is this position in the word, in the sentence. I can do that because I know you gave me the sentence. So I can say this is first position, second position, third position, this token. So I have converted into tokens. The tokens are converted into embeddings, and I have superimposed the position. They learned that adding position was making them even more accurate. So they added this. Then they have this attention layer, which is nothing but just telling you which embeddings are more important compared to this embedding on each one of them. And then they have a neural network. This is what we learned last time, which is just taking this information, taking this as a feature engineering as an input, these metrics, after this multi-head attention has added that context of what is important, which tokens are important to what, that goes to a neural network. And what it splits out eventually is your probabilities of all words of English dictionary. And then the next word, which is the highest probability. And if I can do that again and again, I'm done. And GPT uses just this part of so this is an encoder decoder architecture. Here you use an encoder to encode this information. This is the decoder that you use to generate the next word. In GPTs, we don't use this piece. We only use this piece. So this is not used. You only use the decoder part, and now you can generate next sentences as output probabilities. So that's the architecture. One gotcha that we have is the Financial Times is, so this is the summary. You take the words, you pass through tokenization, you got tokens, you created embeddings. Embeddings allows you to figure out what words come together. Then you put self-attention, which allows you to see where to pay attention, how is each other related. And then you got some encoded output. And then you just take that and pass it to a neural network to figure out what is the best next word probability. And that's how transformers work. This might be a little involved, so I have more links for you. If you want to deep dive, then you can go here. I have put a lot of resources which I have used to learn this. I think this one is what I showed you today. This is a great video to watch. This explains all the math, everything step by step, what's happening in query key value. So watch this, and if you have questions, just put it on Scrumler. I can take that. These two videos is all you need to do. So this is just what I did together with you. And if you watch this video, this will make you almost 95% graduate in everything machine learning that is going behind the scenes. This is a good blog which explains the math and how it is done. So that is the other one. And then if you're curious, you can watch all the videos of how this transformer gets to LLMs, then how GPTs, how attention works, how memory in LLM works. These are 4 more videos. I have some announcements. January cohort will be starting in January, of course. And we are doing the early bird now. We have stopped the bonus 2-in-1. And next time, we will be talking about knowledge graphs. Okay, now we have some idea of transformers. So let's have a discussion, which is, what is so important about transformers? This question, what's now and what has changed, has 4 answers. Now you know a little bit about transformers. Transformers allows you to do scaling of self-attention. They have this idea of attention, which allows you to figure out, given a set of words, which word are important and which words are not important. And when it does it, it can do it in parallel. And that allows it to predict the next word faster or more accurately. That's pretty much it. That's all you need to learn about transformers. If you know that, then, hey, we have these 2017, 2018 that this paper comes out, which allows people to do transformers. And if they have parallelization, then what you can do is you can actually come up with something called scaling laws. The more attention layers you can add, we just talked about single attention. We have multi-head attention. So we have many layers of attention that allows us to learn many things about which words across different things I can focus. And then I can combine, I'm even better. So that scaling law says that the larger or the more attention layer, the larger the neural network you put, the more things you can learn. And you keep growing that network, the more learnings you will continue to have. That allows us to build models which are larger and larger in size without creating new architectures, without hiring more PhDs to research how to encode attention. The scaling laws says that the larger you make the models, the more accurate they will be in doing predictions. That allowed GPT-2 to GPT-3, GPT-4, GPT-5, GPT-6. And then on top of this, we have done some more reinforcement learning with human feedback, which is giving us some sense that we are having some human-like interactions, which can solve a lot of problems. So one reason of why now, why, how is this idea of this architecture, which allows us to encode attention better. If it allows us to do attention better, plus scaling, that the more layers you put, the more attention or more better the predictions become, or the more human-like it becomes. That means we have a small feeling of AGI in our hands. That was never there. Because if you wanted to do recurrent neural network, which was that doing 1, 1, 1, 1, 1, it was just taking 5 years to train this model, or 20 years, and who was ready to wait 20 years. But now if I can put more GPUs, as it's happening in parallel, I can do everything faster. The more the data, the more the GPUs. That means the more the compute, the more I can go and get closer to this AGI thing or this human-like interactions. And that has changed, which has made where we are today. So that answers one aspect of it. Let me give you another one, which is,
it is a workload.
This is the only architecture which can encode everything into tokens. So we can encode audio files, we can encode images, and we can encode text. What that allows you to do is, that allows you to pay attention not only to just one dimension, which is text, but how this text relate to this image, how this image relates to this sound, which is how we think, right? I am talking because I'm looking at all of you, and because I am talking in this language, but I'm able to understand you also, right? So I'm doing all the three modalities. But this is the first time we have a single architecture which can allow us to build multimodal systems. That was not possible before. We never could build multimodal without transformers, and transformers allowed us to build multimodality. With multimodality, we can go and build this. And now we can think of AGI, because multimodality is a primary focus of if we want to build something like human intelligence, because we don't think in text. We think in text, images, and sound. And this is the first time we have an architecture which can think in the same dimension. So everybody is unifying to that one thing. If we can do that, then the last thing here is that we have a lot of data which does not require human labeling. So I can train these transformers on the internet, and I know what the next word is. And if they become good in sequence to sequence without human labeling, I have a biggest unlock in humanity's history. Because if you wanted to train convolutional neural networks, which is images, they wanted humans to label everything. There's a movie on Netflix, I believe. It's called Human in Loop. It's a story of an Indian woman figuring out her life while labeling things. And you can see how she labels where the eyes are and where the things are, because that's what was needed. But in this, you have a lot of training that can happen without human feedback. That means all you need is machines. And this is the other thing that has happened that has never happened before at Transformers, that allowed us to do without labeling. Means we tried with RNN, we tried with LSTM, but they can't parallel process. You got like 3 takeaways, which is, hey, what are transformers? Transformers are basically a way to encode feature engineering, but put self-attention. And that, how you calculate that is the another unblock. Can I calculate this parallelly? Each word can calculate parallelly. And now you are seeing that quadratic answer, that the more context you add, my name is Mahesh, then the calculations, if this is your context window was only this, then you have to do this many calculations only, right? But if you add one more word in the context, which is my name is Mahesh and I am cool, let's say I add 3 more. It doesn't, now everybody has to go to this word, right? And everybody has to go to this word too. And this word has to go to everybody. So each word adding is going to increase your compute power, at least in the beginning, to pay, even calculate the attention, the values here to quadratically. So now the more you add, because everybody needs to go talk to everybody else, This is the disadvantage where the context length is limited, because each word added has to go and talk to every previous word, and every previous need to go and talk to this word to calculate their attention score or self-attention score. So that's the answer to this question. Can these models think or reason? How you think about that now? Now you know a little bit about how they are working. They're predicting the next word. That word can be anything that is in the English dictionary based on some neural network. If you feed this attention layer inputs, then it works. Otherwise, it will not work. So that's what is happening behind the scenes or underneath with first principles in these models. Can I hack this to, instead of depicting what the answer is, before that, can I first say, hey, to answer this, what is your plan? And depict the next word in the plan, and then use that plan to do the thing in which some dumb human like me will think I'm thinking, but behind the scenes, I am still predicting the next words. But what kind of words I predict first? First, I go and predict the word of the plan, and then I use that to do the thing that the user told me. While the user doesn't know behind the scenes, I'm doing it in 2 steps, then they can think that I am thinking. And that's the idea of, hey, can you think or reason? That means, is this a hype? No, right? If we can improve chain of thought thinking, like the models to do better planning and better reasoning, if we can train models on different planning, even with the current technology, we will be able to do a lot of work which humans are doing. And to be honest, I am not really good at planning either. I just go do things. And we will be able to mimic a lot of those humans. And if we can do that, then we will be able to elevate humanity to one step forward, or push them to think even harder, because we are coming and thinking like them, because we have a lot of data on how human planned and think on each task. And if we don't have data, we have humans to feed into this. And if we feed it, there are finite number of things humans are doing today. We are not doing infinite things in the world. And if we can take all those plans and train these models, then we can do planning. That means we can continue to have more and more impact of AI. That means maybe it's not an hype, and maybe I should stay happy. Maybe as we go in the years, maybe we're just like, I don't follow the hype into, I'm not saying the hype is not in the stock market, but just the technology has it. And now you can make your choices for products too, based on the information we have. Now, last question, why tokens, not word? The idea is this one, which is we are trying to learn as much as possible, but we want to give some structure to machines. Machine cannot take randomization, because if you give them unlimited characters, now you say memorize is 9, then 6, they need, we learned that if you give them standards, they do better. So we will have to give standard. Now, can we give character level standard? Then it won't learn anything, because characters have no information in it. Okay, if we give sentence level, then finding a lot of sentences which are similar on internet is hard, right? Because our sentences differ a lot. So we want to go to word, but the words can be of larger size. So that's second piece, which is we want to give standards. So one tenet is we want to give a standard size to machines. Second tenet is we want to have patterns. If you put these two tenets, that's why we came up with a token size of 3 or 4 characters. And we give each token to these commas or dots or question marks, so that we can learn these patterns. We're just mimicking how the world on internet is, so that we can learn without human labeling. And that's why the idea of tokens, and that's why token exists. I hope me going through my own question and then answers help you understand a little bit about tokens. I can go into a little bit more technical debates, what the query. One question I will leave you with, and then we will call this a session, is, Mahesh, you are saying self-attention is everything, but then can you break it down on how I know that these words I should pay attention to and this one I should not? How is that done? That question I didn't unbox today. That's in that video that I gave you, the second video in the slide. And that answers that question in a whole 60 minutes video. So I would like you to watch it. And if you don't get it, then we'll come back. There's this idea of query, key, and value, 3 metrics that your embeddings need to multiply, and they allow you to encode what to focus, what not to focus. And that is what attention is. Attention is the value of query, key, value taken together. And that is learned to figure out where we pay attention or not. So I leave you with these three terms. Attention, I think all of you got, but attention is how attention is calculated depends upon query key value. So now what is query, what is key, what is value is open questions, and rest all product specific questions you have answers to. And I think my goal was to make sure that you know a little bit more about transformers that you knew before after this session. And if I achieved it, do let me know. If I failed, please use it at Slack or LinkedIn to let me know how we did. Thanks a lot. This is all I had today. I know I took more than an hour, but I hope it was useful.